most important part of the assessment, evaluation and strengthening process is the assessment, because that sets, among other things, whether you need to do anything in the first place, and it also probably tells you, if it's done properly, where best to spend your money on the strengthening process if that's necessary. Now I'll give you my credentials. I am a fellow of Engineering New Zealand, what used to be called the Institution of Engineers. I'm also a fellow of the New Zealand Earthquake Society. I was a member of the panel that wrote the set of guidelines for both the ISA and the DSA. More about that in a moment. So I think I know a little bit about the documents, having slaved over them for about 4 years and having written the first one in 2006 as well. There are two kinds principally. One is the so-called initial seismic assessment, or the other is the detailed seismic assessment. Both are defined procedures in the document Seismic Assessment of Existing Buildings, written by the New Zealand Society for Earthquake Engineering for the Ministry of Business, Innovation and Employment. And that document was promulgated in its final form in time for the legislation in 2017. In either case, the objective, the purpose of the assessment is to predict the onset of an ultimate limit state, which is the maximum achievable strength of a building or its maximum deformation capacity. The two, you can use either process, provided that when the ultimate limit state is reached, the building may very well collapse and cause injury or death to people in or around the building, or damage to other property. Now, that proviso is often overlooked. So if a building reaches an ultimate limit state and is not going to collapse, then it's not earthquake prone. If, on the other hand, is likely to collapse and is not likely to cause death or injury to people, then it's not earthquake prone. This is taken into account a little in the legislation by exempting remote churches, for example, that are only occupied perhaps 1 hour a month. But it's something that should not be overlooked. Attainment of the ultimate limit state is expressed as a percentage of the strength or stiffness of what would be required for a new building of the same type on the same site, as Karen has already mentioned. It's expressed as an X% of new building standard for the given importance level Y. That's, the importance level is 1 for a low importance building like an isolated farm building, which you probably would never do an assessment on anyway, but some people do. Buildings of ordinary importance are importance level 2, and they're things like offices or small shops. Buildings with higher occupancy, such as buildings like here, where you might have up to 300 people in the Opera House, are importance level 3. Importance level 4 are buildings of prime importance to the recovery after an earthquake, like surgeries or operating theatres. Earthquake proneness. A building is defined as being earthquake prone if the ultimate limit state is reached in a moderate, that should say, not modest, earthquake. A moderate earthquake is one that produces an intensity of shaking at the site that is 1/3 as great as the intensity assumed for a new building of the same importance on the same site. So an example, so an earthquake prone building has a rating of 33.3%, not 34%. Not that it matters at all, because you'd round these numbers anyway. And for Phil's information, the 65% is rounded down from 67, because that's where the New Zealand Society for Earthquake Engineering first pitched its strengthening process. Now, that was later adopted by some councils. If it was earthquake prone, in other words, less than 1/3 NBS, then you had to strengthen to 2/3. That's what the many councils adopted. For example, Greymouth, Nelson, Christchurch after the earthquake. But people were astute enough to say, well, it actually says removing the danger. What is the danger? The danger is collapse in a moderate earthquake. And if you remove the danger and get to 34%, let's say, then you remove the danger, and councils have got no right to go any further. Now that was originally the subject of a judicial review, but now it's in the legislation, thank goodness. So you don't have to go more than 34%, except for the reasons that Phil suggested. The ISA using an IEP, that's an initial evaluation procedure, is intended to screen out those buildings that are not earthquake prone. So it's the other way around, rather than prove that they are earthquake prone. It is therefore a rather conservative assessment. The rating therefore tends to be lower than more detailed procedures are likely to rate the building. Here are a series of slides which is simply bookwork for the IEP. The first page just says something, what about the information that you've got, where the building is, what its address is, some floor plan or something like that, a photograph or two to describe the building. The next one says something about the date of construction, the sort of ground that it's on, and so on. Then you start stepping through things like how ductile is the building. In other words, once it reaches some yield plateau, can it then accept further deformation without collapsing? And that is done for each of the two directions, principal directions of an earthquake. Let's say parallel to a street and normal to a street. And having worked through all of that and decided whether there are issues with pounding of against adjacent buildings, and if that is an issue, or whether it's on liquefiable ground and these sorts of things, you then come up with a rating. And if the rating is less than 34%, then it's earthquake prone, and if it's not, then it's not. You also, then there's another category here, which is about earthquake risk buildings, which is a sort of subcategory just for interest. Is it greater or less than 67%? Which is of interest, as Phil says, to others, which I'll get to later. Then a final summary page. The detailed seismic assessment, on the other hand, actually uses specific calculations of the same sort that would be used for the design of a new building, but with modified parameters. For example, you don't use the guaranteed minimum yield strength of reinforcement or structural steel. You use rather the mean, which is higher. You don't use strength reduction factors for the assessment of the strength, say, of a beam or of a column. You use a strength reduction factor of 1. So these modifying things automatically get it higher before you start. You can use approximate methods that have been demonstrated to give the right result, or you can use very sophisticated methods for the attainment of the ultimate limit state using a three-dimensional model with a simulated earthquake applied to it. That is what we do most of the time. We do a proliferation of IEPs. A lot of our assessments in Oamaru automatically seem to get above 35%, and that's because of the low seismic zone for Oamaru. Inland, where you've got higher seismic zones, that's not always the case, and it's very seldom the case in places like Queenstown, or let's say a Greymouth with a zone factor of 0.45. Here it's 0.13. The simple detailed seismic assessment procedures for a single or two-story building with a flexible diaphragm, you can apply an analysis along separate framing lines. Let's say one external wall, an interior wall if there is one, the other one, without taking into account what the whole building is doing. In other words, things like torsional movement of the building, you simply ignore. And then you can also use a displacement-based procedure for parts of the building or for the whole building. And many engineers don't use that because they don't understand it. For parts, these include face-loaded walls, such as walls supported at the top and bottom of a story, or even cantilevered walls. And cantilevered walls around Oamaru are very useful. Cantilevered walls are especially important for Oamaru because Oamaru stone walls are usually thick for their given height. You know, quite typically around Oamaru, as you all know, you have walls half a metre or 600 or even 800 thick. and they're only perhaps 6 metres tall. So with a height to thickness ratio of around that, if there's nothing, if it's not holding up the rest of the building, it's just holding up a lightweight floor, for example, it's automatically there. Here is an example of a simple spreadsheet which looks at a wall which is 1/2 metre thick and 5 metres tall, and you see there the percentage NBS in the light green box near the end just before conclusion, low risk, it's 96%. Now, if that was in Greymouth, it would be a lot less because it's proportional to the zone factor. And if it was inland at Curragh, it would be less, but it certainly would never get to the earthquake prone, unless it was a lot of mass being held up from within the building. This one is because it's most recently topical, and it was an assessment we did via Bill Dean for the Waitaki District Council, who by this stage had agreed to purchase it, and they can tell you more about that. This is what it looks like in a three-dimensional model. That's what it looks like without the roof, because it gives you a better idea of what it looks like. And you can see it's quite cellular in nature, and those inner walls are 1/2 metre thick. And that's what it looks like from the back. When you apply an earthquake to it, that's an idea of how it deforms. And this is before the strengthening went in. And if you look towards the bottom, where it says step time 0.648, let's say 65%, it was already 65% without applying an importance level of 1.3. The Ministry of Justice required that the importance factor be 1.3, and it didn't matter how much we argued over that, it was 1.3, and they wanted 67% of the importance level 1.3, so we had to strengthen. Waitaki District Council, on the other hand, said, if we're going to own the building, it would be nice to have an importance level 1.3 at 100%. So that was achieved with no real increase in the cost of strengthening. That, the darker patches give you an idea of where the joints in the blockwork or in the Oamaru stonework open up. And it's by no means everywhere, and that's for earthquake parallel to the street, in other words, that direction. This one we've also assessed in Oamaru. It's category 1. It's St. Patrick's Basilica. That's it without the roof on, so you can see how vulnerable everything is, particularly those long internal walls that are just supported on columns. So there's not much lateral restraint. And in this one, we actually did a time history analysis. That there is at 2 seconds into an earthquake, which is 15 seconds duration. It's all going in one direction. This is at 4 seconds. You now notice that it's not going all in one direction, but the walls nearest to me, coloured blue on the top, are going in one direction. The ones on the far side coming towards me are red. You notice that the front turrets are now starting to creep towards the street as well. This is much further on at 5. It doesn't get much worse than this, but now the creep of the turrets towards the front is. Now this is very sophisticated engineering, but well worthwhile for this particular building. We managed to show that it's 80% or more of. So if the church ever needed to refinance it, I'm sure the financiers would find that satisfactory. This is the Dunedin Railway Station, which I have already filed the results to the DCC. They've come back with some supplementary questions, but that is the model for it, and you can see how detailed these models have to become to capture all of the detail, such as things like dormers, turrets, parapet blocks, and so on. You notice in this case we've even modelled the piles. Which process to choose? Use the initial seismic assessment if you're only interested in whether or not your building is earthquake prone and to satisfy the legislation. If you get a sufficiently high grade, for example 67% NBS, if there's change of use involved, because that usually requires nearly as reasonable practical to the same level as for a new building. Most councils will accept 67%. And if you've got limited financial resources, for example, an initial seismic assessment will typically cost $2,000, at least in our office, and for a mid-sized building, a DSA about $8,000. Use a DSA if the ISA suggests potentially it's earthquake prone and you want to avoid the costs of upgrading. Use an ISA if the ISA suggests it's earthquake prone and you want to be able to plan the best way to strengthen, because that can be built into the three-dimensional model. Your new structure can be built into the three-dimensional model and you analyse it again. If the ISA suggests it's not sufficiently high for a planned change of use, and repeat what Phil said, if the financier, insurer or tenant requires it. Government tenants, for example, require 80% in our experience. Most others are now focusing on about 67% on renewal. Now, how do I strengthen? I would say assess using the displacement basis first and then put your strengthening in and see how it goes. ECOMOS is an international convention on monuments and structures to which New Zealand is a signatory. And it talks about, among other things, reversibility. So whatever you do to a building, you should be able to reverse it. So that tends to suggest that you use structural steel rather than concrete. You don't submerge a beautiful Oamaru stone building in concrete. And I would first of all target maintenance and then interconnection. In other words, repair what's deficient, because that will be taken into account in the assessment. And then interconnection, by that I mean getting floors to connect to external walls, not so much to internal ones, less important, but to external walls, so that, for example, if the walls spread apart, you don't lose the floor downwards because it falls out of ledges and things like that. Do not deface, and parts often control the percentage NBS. So target those parts first, and these include parapet chimneys and ornamentation and all sorts of other things. Special considerations for Oamaru stone. Stone walls are usually quite thick, so are inherently stable. Oamaru stone is soft, so expanding shell anchors like true bolts and things like that don't usually work particularly well. But epoxy has improved in recent years to such an extent that they can be quite reliable in Oamaru stone. It didn't used to be. Options for under-reamed anchors are self-drilling anchors that make a little bell at the end, are now reasonably easily found. There's also screw anchors, which are showing quite promise because they're available quite long. You can get them a long way into the stone. Upgrading diaphragms is usually ineffective in Oamaru stone buildings because the stone weighs so much, and really most of the mass is in the stonework. Even as a building as a whole, with quite a large interior space, the weight that's on the floor and the floor itself adds very little mass, and usually the walls themselves, particularly if they're cellular in nature, just about take care of everything. One case in point is the Bryden Hotel across the road, where it's nothing like earthquake prone. It's something close to 100%, because when you look at it inside, there's a lot of interconnecting walls. Percentage NBS is often set by the parts rather than the overall rating, and concentrating or improving the parts is often sufficient.